Let's examine another binomial distribution problem. Suppose we're still considering the same manufacturer where the supplier produces 10% defects, but this time we sample 20 items. The value of P is still 0.10. But now we want to know what's the probability that we would get exactly 5 defects. Now that we understand the binomial probability formula, we can solve this much more quickly than writing out all possibilities. So using our binomial probability formula, we would have the combination of 20 things, that's n, taken 5 at a time because we want 5 defects, times, well, 0.10 is the probability of 1 defect, and we want 5 of them, times 0.90, which would actually be the value of Q, which would be the probability of getting a good part. And this value right here is 15. That is, if we want 5 defects out of 20, then we are going to have 15 good parts out of 20. When we work this out using a calculator or a computer, we get 0.0319. So how many defective parts would we actually expect to get out of 20 parts? Well, if we go back to the mean of the binomial distribution equals n times p, in this problem, n is 20. We sample 20. We have a 10% defect rate. 20 times 0.10 is 2. We expect to get, or average in the long run, 2 defects out of 20 if 10% of the population are defective. In our particular problem, we got 5 defects out of 20, which is quite a ways from the average. The probability of getting 5 defects out of 20, when you really should be getting 2 of them, is about 0.0319 or 3.19% of the time. So why would this actually happen? Well, sometimes when you are producing 10% defective items, you will get 5 out of 20 defects, and other times you'll get 0 and 1 and 2 and 3 and others. How often will you get 5? About 3.19% of the time. On the other hand, it's possible, since we only did this one time, that this may indicate that the value of P is no longer 0.10. And that's something we'll consider later on in this course. The possibility that maybe P is 0.20 or 0.25 or 0.30. So the low probability can indicate several things to us and is useful to us in making decisions in the business world. Several centuries ago, it must have occurred to mathematicians that it's somewhat a waste of time for people all over the world to be computing and recomputing binomial problems, doing the same kind of problems over and over. Because if we're sampling 20 parts and 10% are defective, or if we're sampling 20 consumers and 10% of them are left-handed, it's really the same problem. So for several hundred years, mathematicians have been writing down answers, and they've created tables that we call the binomial tables. And so we want to look at how to solve for binomial problems using tables. So let's go back to our last manufacturing parts problem where we had an n equal 20 and a p equal 0.10, and we wanted to know the probability that x equal 0.5. Well, we have associated with this course a whole set of binomial tables. How do we go about using them? Well, the first thing we do in the binomial tables is we look up the value of n. So we would go to the tables where n equal 20. Once you get to that set of tables, then we want to look up the value of p. It's not called p in the tables, it's called probability. So we have probability and several possible values, starting with 0.10, 0.20, 0.30, and so on, all the way to 0.90. Then over in the left column, we have x or x values, 0, 1, 2, 3, 4, 5. How many values do we have here? Well, out of 20 parts, we could get all 20 defects. So the values of x will go all the way to 20. Our particular problem, we want x equal 5 from n equal 20. So how do we get the final probability value that we have here? We go to our column where p is 0.10, and we pick out the value of x that we're trying to solve for, x equal 5. And from there we can get our answer, which you will see is 0.032. When we solve for it using the binomial probability formula, we got 0.0319. Of course, there's virtually no difference here. It's a matter of rounding error. The binomial tables are especially useful if you have what we call cumulative problems. The problem that we just showed you was we had x equal 5, which is what we call an exact problem. Let's look at a cumulative problem and how we could use the binomial probability tables to help us solve it. Suppose that 60% of all mall purchases are via credit card. Suppose further, we randomly sample 15 customers. What is the probability that 7 or more of the 15 customers use credit cards for their purchase? In other words, what's the probability that x is greater than or equal to 7? In solving this particular problem, if we were to use the binomial probability formula, we would have to solve for 1x at a time because that formula can only handle 1x at a time. Because there are 15 customers and we want the probability of getting 7 or more who use credit cards, we would actually have to solve this problem as x equals 7, x equals 8, x equals 9, and so on, all the way down to x equals 15. Using the formula, and by way of review, we would have the combination of 15 things taken 7 at a time for this particular problem, times 0.60 to the 7, times 0.40 to the 8, and we would have to do this for all these problems. So in this particular instance, using the tables is really advantageous. So let's figure out and determine how we can work this problem using the tables. So in this particular problem, we go to the binomial table with n equal 15. We go to a probability, or a value of p, of 0.60. You'll notice in the table that the values of x start at 0, and they will go all the way to 15. We're interested in the probability that x is greater than or equal to 7. So we go to our column where p is 0.60. So the particular values that we are interested in are x equals 7, 8, 9, all the way to 15. Using the table, the value for x equals 7 is 0.118. The value for x equals 8 is 0.177. The value for 9 is 0.207, and so on as we go down the binomial table. And when we get through, we can total these values, and the value total is 0.905, which is the total of the probabilities for x equals 7 through x equals 15. So the answer for this problem is, if I'm sampling 15 customers, and if 60% of the customers use credit card, the probability that 7 or more of these customers will use a credit card is very high, 0.905. One of the things that you should know about binomial distribution tables, particularly in this book, is because of space limitations, the tables do not contain all values of p. You probably noticed when you looked at the binomial tables that the probabilities at the top of the table, or the values of p, were 0.10, 0.20, 0.30, 0.40, and so on. Suppose we're working a problem where p is 0.44. Well, it turns out that you can't use the table for this particular problem. So if you have a binomial problem where p is not 0.10, 0.20, 0.30, and so on, you're going to have to use the binomial probability formula to work out the exact problems. Now let's summarize what we've learned today about the binomial distribution and solving for binomial distribution problems. The first thing is that binomial problems have an n that's greater than or equal to 2, and when we have 2 or more that we're sampling, we get into what we call multiple sequences, and we have to account for that. The next thing is that in each binomial problem, for each individual item or person, there are only 2 possible outcomes. And we already know the percentage of the population in general that have these particular characteristics. And we denote that by p, which is the probability of success. And because there are only 2 possible outcomes in any one instances, then we have q, which is the probability of a failure. And that particular probability equals 1 minus p. We also learned that the binomial probability formula consists of the combination of n things taken x at a time, p to the x, and q to the n minus x. With this portion of the formula yielding the probability of an individual sequence, and this portion of the formula telling us how many sequences. The other thing we learned today then is that the long-run average, or the expected value of a binomial distribution, which is mu, equals n times p.